Okay, so what we're going to do in this mini lecture is I'm going to introduce you to two key concepts in chapter 12 of Orris's book. And those key concepts are the Pearson correlation coefficient and simple regression. But the way that I'm going to introduce you to Pearson correlation and simple regression is to first go back to chapters 10 and 11 and frame the difference of means test and ANOVA based on scaling of data. So when we do the difference of means test, we're actually working with two variables, a two-level nominal variable and then a variable that's either interval or ratio, okay? When we do ANOVA, we're working with a nominal variable that's three or more levels, and then the second variable is interval or ratio. And the way I want to now frame the difference of means test and ANOVA is I want you to begin to think of those as tests of differences, okay? In the difference of means test, we were asking the question, was an observed mean equal to or different from an hypothesized mean? Or in the two-group difference of means test, we were asking whether two groups had means that were equal to or different from one another. So listen to the preponderance of the word difference in what I just used to describe the difference of means test. And the same goes for the ANOVA. And remember, the ANOVA in some ways is just an extension of the difference of means test. Here we can only assess whether two groups are equal to or different from one another. But when our nominal variable goes to three levels or more, in order to assess whether those groups are all equal to one another or different from one another, we have to do ANOVA. So difference of means test and ANOVA, you're going to view those as tests of differences. And then just a real quick review, our null and alternative hypothesis here would be mu1 is equal to mu2, or our alternative, mu1 is not equal to mu2 in a two-group test. If our three-level nominal variable had three or more groups, we'd go to ANOVA and it would be mu1 equals mu2 equals mu3, or mu1 does not equal mu2, does not equal mu3. And in these tests of differences, we're observing a sample mean to draw inferences about a population mean, okay? So we observe a sample mean to draw inferences about the population. Everything I've said there should be reviewed. Now, I want to go over to the Pearson correlation coefficient. Orris doesn't give as much attention in chapter 12 to the Pearson correlation coefficient as I probably will in the mini lectures, in my memos, and in the class. But I want to make sure that we develop a really good understanding of the Pearson correlation coefficient, because that's going to build the basis for when we go on to learn simple regression. So notice in the Pearson correlation coefficient, I say that both variables are interval or ratio in scale. Okay? So anytime you run into a question where both variables are interval or ratio in scale, that should be a signal to you that it may be a time for us to do the Pearson correlation coefficient. I should mention also that the Pearson correlation coefficient is just another inferential statistics tool that you'll have in your arsenal when you leave the class. And I described the Pearson correlation coefficient as a test of association. Now at this point that may be abstract to you, but as we begin doing some exercises in Megastat and so forth, you'll begin to see why I make the assertion that the Pearson correlation coefficient is a test of association. So where the difference of means test and ANOVA gives us tests of differences, in the case of the Pearson correlation coefficient, it's a test of association. We're not testing to see whether two variables are different from one another. We're testing to see whether they're associated with one another. And the null and alternative hypothesis for the Pearson correlation coefficient is actually very simple to write. This goofy looking P, which is the Greek letter rho, so for our null hypothesis, we say that rho equals 0. And for our alternative hypothesis, we'll say that rho does not equal 0. And rho is just the correlation between two variables, okay? And when we do statistics related to the Pearson correlation, we observe the lowercase r to infer the Greek letter rho. Now, I want you to learn that concept similarly to the way in the difference of means test and in ANOVA, we observe the sample mean x bar to infer something about the population mean mu. When we're doing correlation, we observe a correlation between two variables from our samples, which we denote with the lowercase letter r, to draw inferences about the population correlation between those two variables, denoted by the Greek letter rho. Okay? So again, the Pearson correlation coefficient is a big deal. It's the first test of association with which you will work. But what also makes the Pearson correlation coefficient a big deal is it gives us the foundation for the first predictive modeling tool that you'll learn in class. And that predictive modeling tool that you learn in Chapter 12 and in MS 264 is what we call simple regression. Now, the first thing I want to do in introducing you to simple regression is alert you to the fact that similar or the same as the Pearson correlation coefficient, when we do simple regression, both of our variables are either interval or ratio in scale. Remember, with the difference of means test in ANOVA, we worked with two variables, one of which was nominal and one of which was interval or ratio. When we go to the Pearson correlation coefficient, which is a test of association, both of our variables are interval or ratio in scale. Same way with simple regression. Both of our variables are interval or ratio in scale. And then the other thing I want you to do is to begin to build this knowledge base of, we first started out with tests of differences. We now move on to test of association. In this instance here, it's the Pearson correlation coefficient. And then almost simultaneously, we move on to do predictive modeling. Once you have a basic understanding of the Pearson correlation coefficient, understanding simple regression, our first predictive model, will be quite simple. Now, before I close off this mini lecture, I want to show you the basic formula for simple regression. You may have seen this formula back, I don't know, it could be as early as the 6th, 7th, 8th grade. But this is the formula y equals a plus b times x, and that's the basic formula for simple regression. And then I show here where y is the dependent variable. In other words, we're trying to predict the value of some dependent variable based upon x, our independent variable, and then the letter b in our formula y equals b times x. B is the prediction of how much y will change for every 1 unit change in the value of x. And then A is equal to the y-intercept. So this whole whiteboard now really becomes your knowledge basis that will transition us from the tests of differences that we have been doing for the past several weeks in MS 264. We now move on to test of association. We won't spend very much time on test of association, but the time we spend on it is critical because the foundation that you develop with the Pearson correlation coefficient is what will allow you to quickly understand our first predictive model, that being simple regression. Thanks.